Hello, team. My name is Brett Gustafson, and I'm a wireless business developer here at Altera. I'm excited to introduce to you a demo developed by Ankur Vora, a network system solution engineer on our team. In this session, we'll showcase our cutting-edge approach to CSI compression, leveraging artificial intelligence to significantly boost performance and efficiency in modern wireless communication systems. This slide introduces the problem statement for CSI compression as we move towards 5G advanced and 6G networks. On the left, we begin with the 5G network traffic challenge. CSI, or channel state information, is vital for maintaining a robust link between the radio unit, RU, and user equipment, UE. However, frequent CSI feedback, delivered every 10 milliseconds, creates massive front haul traffic. As 5G, 6G aim to support up to 1 million devices per square kilometer, the signaling overhead becomes a serious scalability issue. In response, 3GPP Release 18 has initiated a collaborative effort with over 50 industry contributors. This initiative focuses on standardizing and developing AI-driven solutions to compress CSI data dimensions, enabling more efficient communication between the UE and RU. Finally, on the right, we see AI's transformative impact on the problem. AI models, particularly autoencoders, compress CSI feedback with remarkable efficiency, reducing front haul traffic by up to 100 or 1,000 times. This not only cuts overhead, but also improves link adaptation, saving bandwidth and unlocking broader connectivity, all critical for realizing the goals of beyond 5G and 6G networks. This slide provides an overview of the wireless system architecture which we've implemented for CSI-based communication and analysis. We begin with link level simulation, where we generate a 5GNR compliant uplink and downlink CSI exchange using MATLAB. This allows us to emulate realistic deployment scenarios and test performance under controlled conditions. Next, we have CSI processing at the user equipment, or UE. Here, the UE estimates channel conditions using CSI reference signals, or CSI-RS, and measures key metrics like RSRP, RSSI, and RSRQ. These parameters form the basics of accurate CSI reporting. Moving into the wireless channel, the CSI data is propagated through line of sight, LOS, and non-line of sight, NLOS, conditions, modeled using TDL and CDL, or tapped delay line and cluster delay line, profiles. These emulate real-world channel impairments and fading scenarios. Finally, we reach CSI processing at the radio unit, or RU. The RU decodes the feedback, applies appropriate procoding strategies, and dynamically schedules downlink transmissions to adapt to current channel conditions, ensuring optimal throughput and spectral efficiency. This slide presents the inference network architecture, outlining the full CSI data pipeline, from generation to pre-processing, compression, reconstruction, and final output transformation. We start with CSI data generation, where we create a 5G, 3GPP Release 17 compliant uplink and downlink channel state information using MATLAB. This dataset forms the foundation for model training and real-time inference. Next is the pre-processing stage. Here, raw CSI data undergoes symbol averaging and discrete Fourier transforms, or DFT. This process enhances data integrity and prepares it for efficient neural network processing by converting it into the time domain. Then we move to the encoder, which compresses the pre-processed data using a multi-layer autoencoder network. The encoded output reduces the CSI dimensionality while retaining its essential features. In the decoder, the compressed representation is reconstructed back into its original form. The decoder mirrors the encoder structure to ensure high-fidelity recovery with minimal information loss. Finally, in the post-processing stage, the system reverses the earlier symbol averaging and applies an inverse DFT, or inverse discrete Fourier transform, to convert the data back into the frequency domain, restoring its original structure for downstream use. This architecture enables real-time CSI compression and reconstruction with high accuracy and computational efficiency, making it highly suitable for edge AI inference in advanced wireless systems. This slide highlights the experiment setup and corresponding results, demonstrating the effectiveness of our AI-based approach to channel estimation. On the left, we begin with the experiment setup. We use the Agilex SoC FPGA development kit, interfaced with JTAG for programming, UART for serial communication, and Ethernet for data transfer and power. Our software stack includes the FPGA AI suite for deploying AI model IPs, Quartus Prime for FPGA design, and OpenVINO's model optimizer for fine-tuning AI inference performance. In the center, we have the frequency domain channel response. This 3D plot shows how channel magnitude varies across subcarriers and OFDM symbols, revealing frequency selective fading. Our AI-based method effectively captures this variation, which is critical for accurate channel estimation in real-world wireless conditions. On the right is the PDF versus covariance graph, where we evaluate the correlation between the original and reconstructed channel data using autoencoders. The tight clustering near a correlation value of 1 demonstrates high fidelity, proving the AI model's accuracy in compressing and reconstructing CSI data. Together, this setup and its results validate its robustness, precision, and practical deployment of AI-based CSI estimation for next-generation wireless systems. As we conclude this presentation, I hope you found our insights into AI-driven CSI compression both informative and thought-provoking. I want to thank you for your attention and interest in our work. I welcome your questions and look forward to engaging in further discussion on this exciting area of innovation in wireless communications.